Hello everyone, I'm Ahana Ganguly, a fourth-year undergraduate in the Department of Mechanical Engineering, enrolled in its dual degree course in the specialization of Manufacturing Science and Engineering. I'm a student of Indian Institute of Technology, Kharagpur, having roll number 20ME31058. This presentation of mine is all about my BTech Project 1, which I have worked upon in my 7th semester, that is the semester of autumn 2023 to 2024, under the supervision of Professor Advay Mitra. This project is about analysis of traffic simulations and modeling of specific areas in India. India is one of the fastest growing economies in the world. The average income of Indians is growing, and thereby the number of privately owned vehicles is rising. Though public transport is widely available in India, still it's not sufficient for the population of India. Especially in metro cities, often public transport services are crowded. So to travel peacefully, people are opting for commuting in their own vehicles. And as a result, more vehicles are coming on roads. Poor quality of roads is also one of the causes. This leads to repairs and thereby reducing the usable space. Lack of proper implementation of traffic rules has always been there. So, the main aim of my project is to work on certain model traffic scenarios using a software called PTV VISSIM. Try to analyze those traffic scenarios and fetch datasets from it, which can be fed to several deep learning models, which will help us in reducing the road accidents and traffic congestion in various parts of India. I have created three broad type of traffic scenarios, having signals or not having signals, and the data is extracted from all of them. I have compared the data of all of them with each other in order to get some valuable information. So, the sample scenarios are the following. So, this is the first scenario which I am showing. This will be only for pedestrians, and I have created a pair of models in which I have used signals for the second one and no signals for the first one. So basically the one which I am showing right now does not have any signals. But as we can see, there are certain queue counters, there are data collection points. These two streets are running parallelly to each other but in the opposite directions, and this street is the one which is connecting the first two streets with the help of connectors. Now let us show you the vehicles. From vehicle inputs, we can only see that we have kept the vehicle composition to be pedestrians only, and the volume has been kept as shown from the start of each of the streets. After that, we have specified the vehicle routes. Finally, we have investigated the conflict areas and have created certain conflict rules for the same. So these are the conflict areas, as you can see. The red ones means that the pedestrians here will have to wait for the ones at the green to pass. And we have also reduced the speed for passing in these points so that the people do not overlap or bump into each other. So right now we need the simulation data. So let's start simulating. We are able to see it clearly in the 3D version. Now for simulation, we have to see the parameters part, and in this the period has been kept to be 3600 seconds. And for evaluation configuration, we have kept tick mark in all those points in which we wanted to find out the data. So that's like link and queue at this point of time. Now for evaluation result list, we have to see whether the linked results we can get or not. So basically, if we scroll down, we can see that we are getting the results. That is the density, the relative delay for all of the vehicles, the speed, average speed of all of the pedestrians, and the volume of all of them. Now here, as we can see, that the average speed of the pedestrians is less. This is because pedestrians do not usually have the speed of those of vehicles, and that was said to be around 4 or 5 km per hour. So it's coming out to be that. So we can also get the queue results with this as well. Like if we go to queue results, we will get them. Now the thing is that let me show you the one in which signals are there. So basically, as we have got these, we can see that the queue counters have been set at the same location as that of the one in which there were no signals. There are certain signal heads which have been kept, and these are the same data collection points. So first of all, if we start our evaluation over here, first let us start the simulation. As we can see here that the signal here has turned green and the signals here have turned red. We have used two signal groups over here, and we can get the result list. That is the link results. If we scroll down, we can see that we are getting the density, delay relative, speed and volume. Now the thing which we have to note at this point is that if we look at the report, we can see that we have extracted the data for both of them. Now if we analyze the data, we will be able to find out that the queue length and the maximum queue length for the signalized one is more than that of the non-signalized one. Now this is because for the signalized one, people have to wait for a long amount of time in order for the signal to turn green, and then only they can pass. But this is not the case for the queues in which there is no signal, because people can pass according to their convenience. Also, the density of the vehicles has been like very high in case of the signalized one, and the density has been not so high in case of the non-signalized one. This is also because of the same reason, because like people can pass according to their convenience in the non-signalized one, whereas in the signalized one they have to wait for the signal to turn green and that can pass. Also, if we talk about the speed, that's a vital information, is that the speed is mostly for the non-signalized one close to the mean speed, because people do not have to wait for long times even when they have the possibility to go. But in signalized one, the speeds tend to touch the extremes. Somewhere it is 0.92 or 0.79 or 0.63, and the other points it's 4, 5 or something like that. So this is because like in signalized one, whenever they are able to go, they will be going with their full speeds, and whenever they have to wait, they just have to wait over there. So that's like they will be touching extremes. So this is the first set of scenario. Now I will be showing you the second set of scenario. Let's go ahead. Okay, so this is the second set of models which we have chosen. So it's like we have introduced some signal heads over here, some queue counters over here, and also there are 5 streets, street 1 and street 2, which will be running opposite to each other, street 3 and street 4, which will be cutting the 2 former streets, and there will be another street also, street 5, which will be cutting street number 3. So basically street 5 will only consist of pedestrians, and the rest of them will have both pedestrians and vehicles. Now here we will have to note that we have kept pedestrians also here, which will have an average speed of 5 to 6 kilometers per hour, and vehicles which will be having an average speed of 80-90 kilometers per hour. So basically let's now start the simulation to see what happens. Now since the simulation has started, we can see that there are 2 signal groups, one for these 2 streets and the rest for the 3 streets. Now we can see that the pedestrians are coming, the vehicles are also coming, but one observation we find over here is that because of the pedestrians and vehicles moving in the same path, the vehicles tend to become slower, because they cannot just overlap with the pedestrians or may just bump into the pedestrians. They cannot do that. So that's why they will become slower, and because of which there will be no good speed of the vehicles. Therefore the average speed will be decreased also. Now if we see the evaluation result lists and link results, and if we go down, so here we see that the results are getting evaluated, that is the density, delay relative, speed and volume. If we see the speeds, even though the vehicles are having speeds of like 70, 80 or 90 km per hour, we can see that the average speed is nearly 9 or maybe 6 or maybe 5, because of the large number of pedestrians also which are present. Now let's go to the queue counter. Here also we can see that there is a large amount of queue, like maximum length is maybe 71.30, and average length is 38.21. Now we did the same simulation in a non-signalized software part as well, non-signalized model as well. So what happened in that model, we could not find any that much difference in queue. So like if for non-signalized also, the queue length was almost similar to this one. This is because of the fact that even though here people are having to wait at queues, as we can see that they're still waiting at queues, a large number of vehicles, but in case of non-signalized one also, since the vehicles will be having very large speed as compared to pedestrians and they will be waiting behind the pedestrians to pass through, the vehicles will also form a big queue, and this is because of which the length has no significant difference. So this kind of model we can see in suburban or nearly rural areas where there is no proper management or planning of the traffic or the roads, and people as well as vehicles tend to cross through the same place. So this kind of management, even though which is prevalent in India in certain regions, it should be avoided at all costs, because that is the most unfruitful management we can just ever see. Now let's go to the third scenario, a better scenario from which we can just find out the trajectory of the accident prone points, or maybe the conflict regions where their accidents are possible, maybe the front and the rear coordinates, XY coordinates of the vehicles. We will be able to find out using a software called SSM, and we can use it for further purposes. Let's go ahead. Before moving towards the third model, I would like to speak a bit about this SSM3 software. SSM, Surrogate Safety Assessment Model, is used to perform safety analysis of traffic facilities combining with microsimulation software. This technique may be of use to researchers, transportation engineers, and safety engineers. SSM operates by processing data describing the trajectories of vehicles driving through a traffic facility and identifying conflicts. The vehicle trajectory, that is input data for SSM, is generated by traffic simulation software VISSIM in a trajectory file format which is having a .trj file extension, especially designed for SSM. Then this calculates surrogate measures of safety corresponding to each vehicle-to-vehicle interaction and determines whether or not each interaction satisfies the criteria to be deemed an official conflict. The software uses two threshold values for surrogate measures of safety to delineate which vehicle-to-vehicle interactions are classified as conflicts. These two thresholds are applied to the value of, as you can see, the maximum time to collision, or the time to collision, which we can call as TTC, and the post-encroachment time, which we can call as PET. This SSM utilizes a default TTC value of 1.5 seconds. Once the conflict identification thresholds are identified, the user then presses the Analyze button and simulation data are processed to identify vehicle-to-vehicle interactions which satisfy the conflict classification criteria. So this is the SSM user interface after launching. Now, let us go towards the third model and try to find out the trajectory of the vehicles and the point of conflicts for the same. So this is the final model which we have created. This is a better model as compared to the previous one, actually a lot better, because here we have kept separate places for vehicles as well as pedestrians to pass through. The pedestrians will be passing from these single lane streets and the vehicles will be passing from the double lane streets, these two running in opposite direction and this one running in the perpendicular direction. So let us see the simulation. As we have started the simulation, we can see that there are three signal groups. One is for the pedestrians, and this right now it is green and the pedestrians are passing through. Now as this pedestrians will stop passing when the signal turns red, out of these two signal groups, one will just start operating. So now let us go towards the evaluation. Result lists. Let us go towards the link results. As we can see, for the simulation run number 18, we are getting the density, delay, relative speed and volume. Now here, if we want to just copy this and paste to some XLSX file, we can do so very easily. Now, this is all about the simulation, but there is some other thing as well. Stopping the simulation, let us try to find out the trajectory file of this. Now, for this 18th simulation, we can find the trajectory file which has been created in the place where we wanted to store it. Now let us take a trajectory file for a previous simulation and try to work it out with our SSM software. We have added a particular trajectory file. Let's first delete the previous file. Then we are adding the next file, say for simulation number 12. After adding this, we have kept the maximum time to collision to be 1.5 and maximum post-encroachment time to be 5. Let us try to analyze the trajectory file. And we can find that the analysis is complete. Let's go to the conflicts table. This conflict table shows all the conflict details, including the time, location, and all surrogate measures of safety for that conflict. Along with this, SSM also does another thing, that is, the location where we were supposed to store the SSM files, we had just given a particular location, and in that location it will store another one file. This is the one as we can see, and in this one we can see that SSM will be creating a CSV file in which we can get the X and Y coordinates of the front vehicle and the X and Y coordinates of all the rear vehicles which will be involved in accidents. So this, as we can see, the X coordinate of the front, the Y coordinate of the front, the X coordinate of the rear, and the Y coordinate of the rear. So this is nothing but the coordinates of the conflict points where the accidents can take place when two vehicles might collide to each other from different directions. Here also the vehicle ID will be given, the link ID will be given, the lane ID will be given, and the time steps are also given. Here we can see that front coordinate as well as the rear coordinate Z both are 0 because we are working with 2D coordinates only and not single coordinates. So this is how SSM works. So thus we can see that the Model 3 is one of the best scenarios which is ever possible, because the management of traffic and everything is so proper where the pedestrians or vehicles are not colliding with each other, or neither are they getting slow because of one another. So basically this is how the coordinates of the vehicles which could get involved in accidents and at what time can be generated. This can help anyone studying and analyzing roads to understand the future possibilities of accidents and try to stop the same by taking measures we need. So using PTV VISSIM, I created several VISSIM models symbolizing different real-life traffic scenarios and generated a lot of data from them. This generated data has been stored in the form of CSV and XLSX file. These datasets can give us a large amount of information and can be fed to several machine learning and deep learning models in order to study traffic simulations and road accidents. In future, I will generate some more datasets symbolizing real-world scenarios and will feed the data to deep learning models which will be trained on those datasets to analyze road accidents and traffic congestions and provide fruitful solutions to avoid road accidents. Furthermore, the trajectory of the models will be analyzed to some more extent to find out some extra information regarding the vehicles, such as the safe speed of the vehicles, safe distances between vehicles and pedestrians to avoid accidents, and so on. So this is what my project was all about, and I progressed up to this much in my project. Thank you.